Hi everyone. So we are picking up our discussions. We're trying to finish transposed convolutions today and move to a new model class, recurrent neural networks. All right. So just a quick recap. Here's where we were. We were talking about other computer vision tasks, in particular semantic segmentation. The task of labeling every pixel with a particular category label. We had considered an alternative that we very quickly realized had a bunch of problems, which is that, just do not lose spatial resolution. So if you maintain height by width spatial resolution throughout your convolution network, then you can just make pixel level predictions by using pixel level losses. But this is problematic because doing convolutions at full spatial resolution is extremely inefficient. And most of these convolutions would be, by inefficient, I mean it's extremely slow. It's computationally expensive. And so this idea just simply doesn't scale well. So the kinds of architectures that you see have this sort of encoder decoder sort of decomposition, where the first half of the architecture will lose spatial resolution, gain channel resolution. The second half will lose typically channel resolution, gain back spatial resolution. We know how to do downsampling. It's just add in strides and convolutions or add in pooling layers. We do not yet know how to do upsampling, and that's where transposed convolution layers come in. And we had introduced some heuristic ways of doing upsampling, which was the nearest neighbor upsampling. So just take a 2D matrix and replicate every pixel in a 2x2 neighborhood, or in that 2x2 neighborhood in a particular pattern. We had introduced a particular heuristic, which was, utilize the symmetry of your architecture, and every time there is a max pooling layer, remember where the argmax came from and place have a max unpooling layer and place the pixel at the argmax value. But these are just heuristics. And then what we wanted to do was move towards learned upsampling operations, and this is where transposed convolutions came in. We made an analogy to regular convolutions, or in regular convolutions, we iterate over the output pixels, and we slide our filter over the input pixels. Padding happens on the input, and when stride is greater than 1, skipping happens over the input as well. And all of these things will be flipped. Padding will happen on the output, sliding of the filter will happen on the output, and skipping will happen on the output, and the enumeration will happen over the input. So that's what we were trying to build to. So this is a stride to regular convolution where we are skipping now filters. So strides specify how you slide a filter on the input in a regular convolution. In a transposed convolution, we typically have input size less than output size. Stride is what causes upsampling. So it's a stride of 2, and that's what determines the output size. We still have a filter. The filter is being placed and moved over locations in the output. And this is the right visualization to understand this. So this is the input, X. This is the output, Y. We are enumerating over all X, R, C values. So we are, for R in 1 through whatever, for C in all range, we're enumerating all input values as opposed to enumerating over all output values, which is what we usually do in convolutions. We are placing a particular filter at a particular location. We are multiplying X, R, C with W at that R, C placement value, and we're putting that down. All right. Yeah. And so we also showed you this on a 1D example, and we just the same thing that I showed you on the 2D example. So the input is being multiplied by the filter. It is being placed down at various locations. Whenever there is overlap, things are getting added. And this is being shown at a particular stride, and padding will clip things out. Okay, we said that this is these operations are learned upsamplings as well. So if nearest neighbor is the optimal thing to do, it could be learned. It is present in your model class as a special case, so it could be learned. So what I want to spend today's remaining time before we move to RNNs is to understanding why this operation. It's a perfectly valid layer. Remember that I can have any sort of formal, any sort of mathematical operation that is piecewise continuous or discontinuous or non-differentiable at a finite number of locations. By the way, this operation that I've defined is perfectly differentiable. So it's a valid layer for me to introduce into a neural network and learn the W's, but it's still good to understand, well, why this particular operation. And in order to develop that intuition, let's work at it one step at a time. First of all, why are we calling this transposed convolution? What does transpose mean? What are we transposing? Usually I think of that as a matrix and a matrix transpose. So what matrix are we transposing? And so in order to build that intuition, let's remind ourselves that we can actually have an understanding of convolutions as matrix multiplications if we recall Toeplitz matrices. So if people recall, Toeplitz matrices are these matrices that have constant diagonals. So every number or every diagonal has just a constant value on them. That's what a Toeplitz matrix is, and it essentially says that you can represent a matrix Aij or an entry Aij by the difference in the indices. That there is a two-dimensional structure here, but there's really 1 degree of freedom in your matrix, and so there really aren't. If in an n by n matrix, n squared free parameters, there are only order n free parameters in a Toeplitz matrix. And this is also a construction of Toeplitz matrices. You've sort of seen in your homework. We work you through them in the circular convolution example, for example. But so Toeplitz matrices are quite useful mathematical objects. For us, we particularly care because discrete convolutions can be written as matrix multiplications with the help of Toeplitz matrices. You've already shown this in your homework for circular convolutions. Here, let's just consider regular convolutions, regular discrete convolutions, not circular convolutions. And I claim that this right here is a representation that expresses the convolution operation. So basically, I have this sort of W1, W2, WK minus 1 sort of a sliding operation where the last element has made its way in, and then I shift W1, WK minus 2, and WK minus 1, WK have been placed in. And if you realize what this is doing is this matrix multiplication. So X1 will multiply WK, and that will give me the Y0 entry here, or the Y1 entry here. So I take a filter, I slide it in, and this sliding operation, so for example, this row here, now when it multiplies each one of these entries will give us the particular element-wise product and the sum that we were talking about. So these, I've basically expressed this sliding operation happening here in a convolution, right? That I take a filter and I place it at various locations and I slide it across, and anytime that the filter and the signal overlap, I multiply those entries and I sum them up. I've basically expressed all of those placements as rows of this matrix, and that's how I know that this is computing all of those operations as a matrix vector product. Okay, so that right there tells us that this is so first of all, it tells us this is just another reminder that convolutions are linear operations, because matrix multiplication, matrix vector products are linear operations. Oh, and by the way, this can also be done for two-dimensional objects. So this is, for example, the computation of y 0, 0, and this is the filter being placed on the input. So you can imagine, so this is the, so this filter is w 0, 0. I can actually, by putting in appropriate size holes, so I can, what I put here are the x vec. So I can just string out x 0, 0, x 0, 1 in and all of those pixels here, and this will give me y vec. So the first entry here will be the y 0, 0. So by appropriate zeros being placed, which corresponds to expanding your filter out with zero placements of the filter at the rest of the pixels, you can do this for two-dimensional objects as well. Two-dimensional convolutions can also be expressed as this particular matrix W being multiplied by x vec to give you a y vec, where y vec represents this output y strung up as a vector. So first of all, this tells us that, reminds us again that convolutions are linear operations, whether they be one-dimensional or two-dimensional. But second of all, it gives us a very nice handle into why something might be a transposed convolution. The reason why we can think of transposed convolutions, why we're calling transposed convolutions, is think about this W matrix that we've been drawing, where it has one entry coming in and then two entries coming in, and the filter essentially sliding across the rows. If, for example, I look at what W transpose would look like, W transpose would have this sort of a structure where it would have one element peeking in the first column, two elements peeking in the second column, three elements peeking in the third column, and the filter would slide across the columns as opposed to the rows, right? It would just have a transposed structure. Now think about what multiplication, so we were doing y equals w times x, right? Now think about what w transpose, let's say w transpose x in our case does. If you have x being multiplied here, you have x1 here, x2 here, and so on. And this, now let's consider any particular pixel or the first entry of this. This right here, what it's doing is that it's exactly expressing the relationship that we were talking about, that you take the input and you multiply it by the filter, and anytime the filter is being moved around, and anytime the input multiplies with the filter, anytime there's an overlap, you add them together. And so this operation is it's called a transposed convolution because it is expressed as the transpose of a matrix which is expressing a convolution operation. We'll get to this again in a couple of seconds, that transposed convolution is itself a convolution. Right now on this slide, we're just trying to sort of visually show you the fact that if a convolution can be represented as a Toeplitz matrix with a sliding structure happening on rows, if you take a transpose of that matrix, you will get this sliding structure happening on columns. And then when you do matrix vector product, you will get exactly this intuition happening, that this input was multiplying this filter, because if you just stare at the previous thing, the input multiplying the filter is exactly what you expect to happen in this. So now we kind of understand that transposed convolutions have this particular structure, that if there's a Toeplitz matrix, you take a transpose of that, you get that operation of sliding on the output. The other question that we should address is, what does any of this have to do with deconvolution, and why do people keep sometimes misusing the term deconvolution when what they really mean is transposed convolution? And in order to understand that better, what you have to realize is what is deconvolution, or in our case, more specifically, non-blind deconvolution. Convolution is this operation of going y with x convolved with w. Deconvolution is a formal mathematical operation where you can ask about blind deconvolution. Means that you are given y, produce or compute w, or estimate w and x. And blind deconvolution is an underspecified problem. You have recall that you can express y equals w matrix times x, and if I neither tell you w matrix nor x, and I just give you the output of that, that's an under-constrained problem. And so typically this shows up in things like I captured an image with a camera, and I can express the motion blur that happened as I was taking a picture as a convolution operation, but I don't neither know the parameters of my camera model, nor do I know what the original image was supposed to be like before the motion blur. Can you estimate both my camera parameters and the original image and the clean image? And that's a under constraint problem, and that typically requires making more assumptions. The problem that we are much more interested in is non-blind deconvolution, which means you are given y and w, and you're asked to find or estimate x. And this is a much more constrained problem. So you're given the filter, you're given the output, and you're asked to produce what the input was. This is the formal definition of deconvolution, and it feels like this should be solvable. So if y, let's consider the 1D case again. If the convolution, I can express that as a matrix, clearly it feels like, there are many more, x1 to xn are the unknowns, and each value of y gives me a particular linear equation. I know w's as well. So if you don't have any sort of, if you have sufficient padding happening, it feels like you have plenty of equations with n unknowns. You have n plus k minus 1 equations with n unknowns. You can obviously get a particular solution out. Even if you don't have padding happening, even if you have same sized output, you can still have n unknowns and n equations. So this feels like it should be solvable. But what I'm going to ask and what I'm going to do is that I'm going to make a further assumption that is not going to be true in general, but if it were true, would make our lives easier, and it would also help us make a connection between deconvolution and transposed convolution. So I'm going to make an assumption that let me write this down. So I'm going to assume W is orthonormal or orthogonal. And so basically what I'm saying is assume that the columns of W are that the dot product that they are orthogonal, that the dot product between these columns is 0. And that is not true in general, but it is true sometimes. So for example, if my filter is -1, 0, +1, this is one filter. Does anybody remember we've looked at this filter before? What does this filter do? What does it compute? Just a one-dimensional edge detector, because anytime you have a positive value on one side and a negative value, you have lots of difference. The magnitude of this, the output of this would be large. So now what I want you to do is I want you to think about what the column of this matrix would look like with this as our filter. Basically, I would have a +1 here. I would have a 0 and +1 slid in here. -1, 0, +1 here, and then after that, these are all zeros in this column, and this apologies. And after that, there's a -1, 0, +1 being slided in here. So if I come to you and ask you for this setting of W, actually I should use a darker color so this is visible. For this setting of W's, what is the dot product of these two columns? So column 1 and column 2. Somebody want to tell me in the chat? It's an easy one. Zero. Thank you. Yep. For this setting of W's, we've constructed it in obviously a specific way, but all the ones are multiplying by zeros, the -1s are also multiplying by zeros, and so on. And so the dot product between these two columns is 0. It does not always require +1, 0, -1. I could have also just set up other values so that in the product would be 0. But in any case, for this setting of W, the dot product between these two columns and actually any arbitrary column, any pair of columns is 0. Which means that if I can assume, and it's the norm of the column is not 1, but you can scale the filter so that that is true. I can just divide by square root of 2, and then the norm of every column is also 1. But if this assumption is true, we know that if y is wx, under this assumption, this implies that the best estimate of x you can find is W transpose y. That the transpose of a matrix is its inverse if you assume orthonormality or orthogonality. And we already saw in the previous slide that transpose of the convolution matrix gives you this operation that we've been calling transposed convolution. So this assumption right here is what connects transposed convolutions to deconv. If you assume certain structure in your convolution filters, then you can get that they will invert the operation of convolutions. But in deep learning, we are not guaranteed for any of these assumptions to be held true because W's are parameters. We are learning these parameters by minimizing a loss function, and we are nowhere anywhere holding these assumptions to be true. And so this is just for understanding of what this has to do with deconv. Transposed convolution layers in a deep neural network do not invert anything. We think of them just as learned upsampling layers. But this is just good to keep in mind about why this confusion might exist in literature. Okay. Yeah, I already answered this question on this slide. The last thing that I want to introduce about transposed convolution is, we've learned a lot that transposed convolutions are called transposed because they're the transpose of the Toeplitz matrix. But a transposed convolution is itself a convolution. So a transposed convolution with, transposed convolution with filter W is convolution with a different filter. We can actually express the way transposed convolution is actually implemented is by reusing our convolution implementations. And the way to see that is to realize that if I write down this sort of an operation where I have written x, y, z, so I have this filter sliding in at various levels, and this is my input, and there's this is my output. So this is a 1D convolution kernel with size 3, stride 1, pad 1. And this is the transpose of this matrix. So all I've done is XYZ is now in the column. It is sliding down in the columns. And this is the same thing that it's being multiplied by. The same ABCD that's being multiplied by. And this is the output. notice that just stare at the rows of this matrix, that the rows of this matrix also have a sliding structure. Just like the columns have a sliding structure, the rows also have a sliding structure. And this, the sliding structure on the rows is almost as if you had constructed this for a filter, which was z, y, x. So the filter here that is sliding on the rows of this matrix is z, y, x. The filter that was sliding on the rows of this was x, y, z, right? So that's what's sliding on the rows of this. Transposed convolutions can be implemented as a convolution with a different set of padding and clipping rules, but this is with flipped filters, and this is where the analogy or the equivalence to backprop happens, because we see this behavior happening in backprop as well. One thing to keep in mind is that this clean equivalence happens only if the stride is 1. If the stride was greater than 1, you would not find this clean flipping alignment. But this is important to keep in mind. All right, so that finishes up our discussion of transposed convolutions. The next topic that we're moving to are recurrent neural networks, and this is a new model class. This is a new layer in the Lego building blocks that we are teaching you, but it's also a new way of thinking about new types of data. Everything in convolution neural network lectures has been very centric on images and spatial data. We in RNNs are going to be discussing temporal data. So lots of different kinds of RNNs. So some new words or terms that you're going to hear from us are recurrent neural networks, or RNNs. You're also going to hear in literature or see a term called recursive neural networks, which unfortunately also have the same acronym, or RNNs. But we will tell you that recursive neural networks are a more general family than recurrent neural networks. So they contain recursive neural networks contain recurrent neural networks as a special case. And we'll tell you about the directed acyclic graphs being formed of recurrent neural networks corresponding to chains, and recursive neural networks corresponding to arbitrary trees or DAGs. And you will, of course, hear certain special cases or types of RNNs or recurrent neural networks. Some that, unfortunately, deep learning just is not very good at coming up with names, or this field is not very good at coming up with names. RNNs are also a specific instantiation of the broader family. So recurrent neural networks both refer to the broad family of models, but also a specific instantiation of a model in that model class. There are, of course, long short-term memory networks and gated recurrent units. We will meet all of these. So anytime you see any of these terms, know that this is the lecture you have to come to, and this is the context that we're talking about. And the algorithm that we will teach you is a new algorithm called backprop through time, which is essentially backprop applied to a computational flow graph corresponding to an RNN with a particular form of clipping applied on backprop. So let's start with, in order to get to RNNs, we will start with this question of, why do we need a different layer? Why aren't we done with fully connected neural networks or convolutional neural networks? And the key problem that we are trying to address with recurrent neural networks is that you can't model sequences. As soon as you define an architecture in an MLP or a fully connected neural network, you have an X, you have a Y, and maybe in between you have some number of HLs, some hidden layers. But as soon as you talk about X and Y, you commit to a particular input size. So you commit to X coming from RD and Y belonging to RC. D and C are pre-committed and fixed typically, right? We know how many categories there are. We know what the input dimension is, and we do not get to vary input dimensions arbitrarily during training time. Right? Features are all the same dimension. You don't get to change that. And there's no sort of temporal structure in X or Y that we can model. And by that, I mean, if there was an X1, X2, X3 coming at different timestamp, we don't have a natural way of being able to take care of that in MLPs. And the second problem that we are trying to address is that these are pure feed-forward networks. So we are going from X to Y. We do not, for example, make use of our own predictions. When we predict Y, it does not get utilized. So let's say this is X1 and there is some X2 at a different time. Y1 does not get utilized in order to make predictions about X2. We assume data is independent and that any prediction made about past data tell us nothing about what to do for new data. So there's no sort of memory in the system about what the system has said in the past or predicted in the past. And it's important to model memory or sequences. And here is, for example, my favorite example to go to. I have a couple of characters in front of you. Can anyone tell me what the two characters on the screen are? Regardless of whether you got it right or wrong, what I want you to do is tell me whether your life became easier, whether you have an easier time making the guess now. And I want to say the answer is yes, that you hopefully all agree that guessing what the second and the fourth character is a lot easier. Even though notice that these characters are highly similar, like that the shape is very similar, and they differ in a small number of pixels, and realize that B6A6E, yeah, okay. I will continue with the assumption that now everybody can tell that that's an R and a C, even though nothing about them, about those pixels changed. What changed is commonly known as context. Now that you know that there are other pixels, some of them are representing B, some of them are representing A, some of them are representing E, it becomes a lot easier to read this word in context and therefore infer that those pixels must have been corresponding to a character R and character C. So this is one qualitative example for why sometimes modeling more data, so this is X1, this is X2, this is X3, this is X4, and this is X5. If you're trying to do character recognition, and you know that these characters come in a sequence, sometimes modeling the entire sequence can make your life easier, even if you're going to make predictions at all timestamps in the sequence. Independent predictions can be hard. There can be information in the others, and it's because arbitrary sequences are not allowed. There's something about the data distribution that tells you that there are certain types of sequences that are more likely than other types of sequences. You know that there is an underlying grammar here that certain words can't exist and other words you're familiar with. And anybody who's tried to read handwriting, especially mine, all through this semester knows that it becomes a lot easier if you're looking at a couple of context. So that little squiggle is an N apparently, because that's that word we understand as defense. And I would argue that sequences are everywhere. So sequences show up in handwriting recognition. So this is also known as optical character recognition. So going from scanned images of text to actually inferring what that text is. It shows up in voice recognition, speech to text, where the speech signal is a sequence and the text that you're producing is also a sequence. It shows up in what is known as machine translation. This is what Google Translate does, where you go from one language to another language. And sequences show up even where you might not expect a sequence. So this is a sequence of experiments that were done by these folks, these papers listed here, where they are trying to make a prediction about what character this is, but instead of reading in the entire character as an image, they want to train a biologically inspired glimpse model where you get a sequence of crops of the image. And so think of these as saccades that the human eye might make, where we glimpse at certain areas, and that part of that area where we are looking at is in higher resolution and focus, and others are not. And so this is a way of converting non-sequences into sequences. It is also possible to do that on the output side. So there's a really nice couple of works that do image generation by sequentially generating patches of the image and then merging those patches together. So the output ordering has a sequence, not the input ordering. It's really going to be a spectrum. We're going to use sequences in both. We're going to consider sequences both in input and output. So the, no sequence in input, no sequence in output case, we're going to call the one-to-one mapping case, where this is the standard classification / regression problems that we've dealt with. The one-to-many type of case is going to be where there is no sequence in the input, but there's a sequence in the output. These green boxes are our hidden representations. Red is input, blue is output. So there's a Y1, Y2, Y3, if you will. And think of this as like image captioning, where X is an image and Y is a sequence of tokens that we're producing that describes a sentence for an image. There is the many-to-one case where there is a sequence. There's X1, X2, X3, sequence in the input, but there's no sequence in the output. And this is, for example, sentence classification. If you read a sentence in a review, you have to tell whether it's a positive intent or a negative intent in the sentence, or multiple choice question answering. You can also have many-to-many with multiple variants, where there is sequences both in the input and in the output. And of course, you could have architectures that complete the entire sequence and then predict the output sequence, or you could have architectures where the first one comes in and the first prediction gets spit out. And so these are operating completely synchronously. So machine translation is a common example, where you read a sentence in English and you want to translate it to a sentence in, let's say, German. And depending on whether you want to translate it on the fly, or you first have to input the entire sentence before you can output the translation, it could be this setting or the setting on the right. Video classification is one where you get to read in the entire video and maybe you spit out. Well, that's this one where you read in and on each frame you're saying, is a particular activity happening or not? And video captioning could be another one. So we can have sequences in input and in output. There are going to be two key ideas, and I'll talk about those ideas today. And I apologize, we'll just go over maybe 2 or 3 minutes over 10:45, and then we'll stop. And those key ideas will give us the basis for recurrent neural networks. The two key ideas for RNNs are going to be parameter sharing, that in computation graphs, when we share parameters, gradients get added, which is a very simple idea. We've already met this idea before. We have met computation graphs before, and we have met this idea that whenever you have data or tensors being copied in the forward pass, in the backward pass, when we get so the assumption we're going to make is that there are two different blocks. There was W1 here and W2 here. There were two different blocks. They had two settings of parameters. And the assumption that we're going to make is that W1 is equal to W2, that we're going to share parameters between these two different blocks. As soon as you make that assumption, when you get in backprop the partial of the loss with respect to W1 and the partial of the loss with respect to W2, because you have assumed that these are all equal to a common W, the partial of the loss with respect to W adds up these incoming gradients. This is assumption number one, that parameter sharing leads to addition of gradients. And we've already seen this idea before, that gradients add at branches in the computational flow graph lecture. So that's assumption number one. The second assumption we're going to make is that that we will introduce a notion of unrolling in computational flow graphs with parameter sharing, or unrolling will help us take care of arbitrary time dimensions and not get stuck in loops. Basically, we've always said that directed acyclic graphs can't have cycles, right? That's been the rule number one. You can't have directed cycles. But this is a very sort of broad idea. You'll see this in other classes as well, that anytime you want to introduce a notion of dependency or cycles, you want to introduce a notion of dependencies, but don't want to introduce cycles, you can do temporal unrolling. And this is what that idea boils down to. Let's say I want to do a variable st that depends upon a variable st minus 1 with a function f theta. Now, if I wanted to write this as a computational flow graph, I would say f theta is the operation, is the node in the computational flow graph. And if I am not careful, what I'm saying in a computational flow graph is that the output of this goes into its input, right? That its output is state is s, and its input is also s. But this is not allowed under our formulation of a directed acyclic graph. So the way to handle that, the way to write this as a non loopy graph, is to just introduce a notion of time, that we start with S0 and we have f theta as an operation that happens on it, which produces S1, which produces which goes to f theta again, and this gives us a sequence. Apologies, I should draw this better. Following our convention, that our convention says data flows on edges, and the vertices are always where the parameters live, right? So, S0 is both the input and what's flowing on this, and S1 is its output, which goes to another node, which is f theta, which goes to S2, f theta, and so on. So what we've done is we have expressed a graph that should have loops into a graph that does not have loops. So there are no loops in this bottom graph, and this is a notion of unrolling. We introduced a notion of time. We indexed. So instead of saying S is both the output and the input to f theta, we just indexed with time, and we were able to unroll. And this unrolled graph has a finite length, but does not have any directed cycles. Okay. We've gone a couple of minutes over. Let me stop here. This is where we will pick up next time. We can extend this intuition to having other sorts of input, but this is where we'll pick up next time. So if you want to log off at this point, you can.